Today we are going to discuss an agent-based model that explores the complexities of ecosystem stability. Ecosystems are incredibly complex structures where stability arises from a range of interactions between organisms, their environment and evolutionary history. This model specifically looks at how constraints within an ecological community may form closed loops influencing the stability of the ecosystem over time. So, could you please introduce yourself before our conversation?
Yeah, I'm Stephen Peck. I'm a biology professor at Brigham Young University. I did my doctoral training at NC State in biomathematics, and I've worked in agent-based models for a number of years, and so this has been a lot of fun. I teach a class in agent-based modeling at my institution for graduate students.
To start, could you explain the main purpose of this model and what you aim to uncover, by simulating ecosystem stability?
Yes, this started when I read two books that got me thinking along these lines. I've always been interested in theoretical ecology. And most of the theory in ecology has been derived from regular analytic models or sets of equations and things. And the book I read was by Moreno and Macio on biological autonomy. And what they did is they looked at how constraints work to create autonomous or semi-autonomous systems. And they found that in almost all systems at different scales, what they found was if you have constraint closure, and what they mean by that is that there's a closed loop between the constraints. So one constraint causes something to happen in another variable, and that causes something else. But if it becomes a closed loop, they called it constraint closure. And at the end of the book, they made this sort of cryptic comment. And they said this might work on scales as high as ecosystems. And I started thinking about that because another book I was reading at the same time, this one by Mark Wieland, about ecological theory in communities. And he proposed that we think about theory in terms of four processes: species selection, species drift, dispersal, and selection. He noticed that in population genetics, they really focus on a small set of processes to define how the populations evolve and how population genetics measures can be used to construct theory. And what was really interesting to me was that those two concepts were bouncing around in my mind, and I thought about evolutionary processes as constraints on ecosystem, and began to think about, well, that would be a really interesting way to try to get closed loops, and so to get these constraints to create closure. And so what I did is I created this fairly complex model, but it's all designed to use evolutionary processes to create constraints on ecosystems. And I measured several ecosystem things like stability and evenness and richness in my model. And what I saw was that when I did they postulate that it takes at least three constraints to form a loop. That's kind of the minimum number. And what was interesting about the model is I looked at, as you added constraints, how that affected the model. And I found that right at 3, I began to see ecosystem stability measures start to change and to work as if these were working as constraints. And so for me, it was a nice test of two theories put together that offer some guidance on how how stability emerges in ecosystem. There's a lot of debate about it, even if it exists, or what keeps ecosystems stable, continuous in time, those kinds of things. And this model would suggest that the evolutionary constraints on the creatures evolving in there really do form a constraint that creates the kind of stability that Mario and Massio, uh, Moreno and Massio postulate in their book. So for me, it was pretty exciting.
Given the complexity of ecosystems, I
Uh-huh.
imagine that developing a simulation like this presented unique challenges.
Yes.
And I mean, what were the biggest obstacle you encountered during the model's development?
So for me, because it was a purely theoretical model, and I was trying something that hadn't been done, I wanted to just really make some in principle arguments that this could work. And I think it has to be taken to the field. But because it was so new, one of the great challenges was creating a system that had evolutionary dynamics, ecological dynamics, niche theory, all of these kinds of things came into it to try to create this. And because I didn't have any real world data, because nobody had done this before, testing the model on data was impossible. And I think that provided one of the challenges. But I think the proof was in the pudding, in the sense that just I had theoretical expectations, and these constraint closure should have emerged at about three constraints. And as I added constraints, it didn't change anything. And then I got to three, and I saw these dramatic changes in ecosystem stability and species richness, and all of these cool things that I think really spoke to this is a good demonstration that Moreno and Masio were right about this, and that it's working in this system, which I worked on a lot. It took me about 4 years to build this. It was it is kind of I did it in NetLogo, and so it's a massive model. But yeah, it was hard.
As for the results of the model, what are
Uh-huh.
the key findings regarding, the ecosystem stability that have emerged from the model analysis?
What I saw was that these evolutionary constraints really do act as a, con, create constraint closure. It's really apparent in the model that it's that so it's an emergent model.
Hmm.
I don't aim for anything. I just let the model run. I have these ecological structures in place. I added a couple of ecological structures beyond Wieland's work. I added catastrophe, so that there's times the population takes a crash, and mutation. Those two things are the only two things I added. Um, but what I saw was ecosystem stability, and the measures of that in terms of evenness and stability and richness all really responded in the way that they said it should. And so it wasn't built in. This was an emergent feature of the model. So.
You have made your model available to others through comsys.net. Could you discuss, any difficulties or technical problems you faced in sharing your model on this platform?
So one of the things that's kind of funny is so the graphical display that it shows is only meaningful to me.
Hmm.
What I did is I collected the data as it ran. So it's got kind of the typical NetLogo spatial grid, and all it shows is things blinking in and out of existence. So it's hard to interpret. I actually had to go and use some sophisticated forest modeling to get the results that I needed. So when you look at the model, it's not very exciting. It's kind of boring. And you think, what's going on here? So it takes another level of analysis to actually interpret the model. And I think that makes it hard when people look at it. They see these blinking arrows just going on and off, and even they're meaningful to me. They really helped me as I programmed it to make sure it was working. But as a sort of sexy model showing really cool things in the graphical interface. It doesn't really, it's not very compelling. So
Yeah.
so I'm hoping people read past and see what the model's actually doing and how we analyzed it to learn its value, because I think it really does have a lot of potential to be used on other systems and things.
What are your next steps with this research? Are there or were there any planned follow-up studies or expansions to the model that could further explore ecosystem stability?
Yes, I'm kind of excited about where it's going. I want to look at a specific system. So what I'm looking at is niche partitioning in birdsong. And so I'm creating a model using this so that the evolutionary constraints are all operating on bird agents, and looking at how birds partition the soundscape. So birds will often be quiet if there's too much human noise, or be quiet if other birds are making a lot of racket. And so what I'm hoping is I can actually demonstrate this. And there's lots of good bird data on niches and how the way they partition the soundscape. And so that's where it's going next. And I think that'll be a better demonstration, because it will allow me to access real world data and real world processes. And I'm interested in sound recording right now. I'm trying to get a collection of bird sounds and things. So I'm hoping it'll be a little more realistic and less theoretical, but still demonstrate the same processes.
Thank you very much for your valuable discussion about this model.
Yes, thank you for asking me. I appreciated you reaching out to me.